Hello. Hello and welcome to this video on permutation and combination. In this video, we will solve question number 211 to 220. The link to download the PDF will be in description, and at the end, I will show you how you can download the book as well. So I'll say two things which I always say. First is that when I'm stating the problem, you should pause the video, and only if you cannot solve the problem, you should look at the solution. You can as well skip the question if you don't want to look at the solution and come back later and try it again. The second thing is that you should not spend more than 15 minutes on any particular problem. If you cannot solve within 15 minutes, you should look at the solution or skip the problem and come back later. So without further ado, let's get started. Question 211 says that A is an n-element set. A subset P1 of A is chosen. The set A is reconstructed by replacing the elements of P1. Then a subset P2 of A is chosen, and again set A is reconstructed by replacing the elements of P2. In this way, m subsets are chosen where m greater than 1. Find the number of ways of choosing P1, P2 up to Pm such that P1 union P2 union through Pm contains exactly R elements of A. The intersection of these subsets contains exactly R elements of A. Pi intersection Pj is equal to 5 for I not equal to j. So we consider that there are n elements in the set A1, A2 through An. Now we consider an element A1. Either it is in P1 or it is not. So total number of ways for A1 and P1 is equal to 2. Number of ways in which A1 is in P1 is equal to n is equal to 1, and same for not belonging, that is in one way. Thus total number of ways for A1 and m subsets is equal to 2 to the power m. Number of ways in which A1 belongs to m subsets is 1 to the power m, that is 1. Number of ways in which A1 belongs to none of the subsets is 1 to the power m, that is also 1. Thus, total number of ways in which A1 is not an intersection of subsets is equal to 2 to the power m minus 1. So 2 to the power m is total number of ways, and so we subtract this one. So we get A1 is not element of this. Similarly, A1 being not an element of P1 union P2 union through Pm is equal to 1 to the power m. That is this case. Number of ways in which A1 belongs to none of the subsets. And A1 is element of union is equal to 2 to the power m minus 1. This 2 to the power m minus 1. So the first question is, here exactly R elements of A belongs to the union of subsets, and n minus R elements do not belong to union of subsets. So we can choose R elements in NCR ways, and then this 2 to the power m minus 1, okay, that is this element part to the power R, and 1 to the power n minus R, where A is not part of the set of unions. So total is NCR 2 to the power m minus R to the power 1. The second part of the question is, here exactly R elements of A belong to its intersection of elements, and n minus R elements do not belong to intersection of sets. So the value for which the element doesn't belong to intersection of sets is 2 to the power m minus 1. So here it will be NCR, whether NCR or NCn minus R, both are same. And this power this time will be n minus R and 1 to the power R. So number of ways is NCR multiplied by 2 to the power m minus 1 to the power n minus R. Third case is, I forgot what third case is. Oh, sorry. So the intersection of elements should be 5. Okay. So let Pm plus 1 is equal to A minus union of these sets. Since Pi intersection Pj, this should be J, is equal to 5. Each element of A should belong to exactly one of the m plus 1 subsets. P1, P2, Pm through Pm plus 1. For one element, there are m plus 1 ways. So for n elements, there are m plus 1 to the power n ways. So that is our question number 211. Question 212 says that find the number of ways in which m identical balls be distributed among 2m boxes so that no box contains more than one ball, and show that it lies between 4 to the power m divided by square root of 2m plus 1 and 4 to the power m divided by 2 square root of m. So given number of boxes is 2m and number of identical ball is m. Number of ways to select m boxes out of 2m is 2mcm. Because m balls are identical, they can be arranged in m factorial by m factorial. That is one way. So required number is 2mcm, that is 2m factorial by m factorial multiplied by m factorial. Now we will use mathematical induction to show that 4 to the power m divided by 2 square root of m less than equal to 2m factorial divided by m factorial multiplied by m factorial less than equal to 4 to the power m divided by square root of 2n plus 1. We have not yet covered mathematical induction, so if you want, you can skip this problem. Okay? And you can come back to it later. So first we will show the relation that 4 to the power m divided by 2 square root of m less than equal to 2m factorial divided by m factorial square. So we let Pm represent this inequality. When m is equal to 1, left hand side and right hand side is equal to 1, so equality holds and P1 is true. Let Pk be true, that is 4 to the power k divided by 2 square root of k less than equal to 2k factorial by k factorial square. Now we have to prove that Pk plus 1 is true. That is 4 to the power k plus 1 divided by 2 square root of k plus 1 less than equal to 2 multiplied by k plus 1 factorial divided by k plus 1 factorial whole square is equal to alpha. Now we take the Pk and multiply both sides by 2k plus 1 into 2k plus 2 divided by k plus 1 whole square. That is equal to 2 into 2k plus 1. One moment. Yeah, 2 into 2k plus 1 by k plus 1. So we multiply both sides by 2 into 2k plus 1 by k plus 1. So the 2k factorial will become 2k plus 2 factorial divided by k plus 1 factorial whole square greater than equal to 2 into 2k plus 1, 4 to the power k by 2 square root of k into k plus 1. So this goes to the right hand side and this goes to the left hand side of the Pk. But here we have written left hand side as right hand side and this right hand side as left hand side. So this which we have, we cancel out 2 and this is equal to 2k plus 1, 4 to the power k by square root of k plus 1 is equal to beta. Now we divide beta by alpha. So when we divide, that is equal to 2k plus 1, 4 to the power k divided by square root of k into k plus 1 into 2 square root of k plus 1 by 4 to the power k plus 1. So we write the left hand side of alpha here and reciprocal. That is equal to 2k plus 1 by 2 square root of k into k plus 1, which is equal to 2k plus 1. We bring 2 inside, it is 4k square plus 4k, which is equal to square root of 4k square plus 4k plus 1 by square root of 4k square plus 4k, which is greater than 1 and hence beta is greater than alpha. Now similarly, we take the condition of 2m factorial by m factorial square less than equal to 4 to the power m by square root of 2 to the power m plus 1. We denote this by qm. So when m is equal to 1, left hand side is equal to 2 and right hand side is equal to 4 by square root of 3. So left hand is less than right hand side, which makes q1 true. And we again assume that qk to be true. And we have to prove that qk plus 1 will be true. We let it as x. Now we multiply qk with 2k plus 1, 2k plus 2 divided by this should be k plus 1 whole square. R is extra here. So we multiply with k plus 1 whole square, and our left hand side here, when we multiply with this, left hand side becomes 2k plus 2 factorial by k plus 1 factorial whole square. And this should be k, this should not be m, okay? Which is less than equal to 4 to the power k plus 1 by square root of 2k plus 1, and then the multiplication factor. And we let this to be y. Now we divide y by x, and similarly we obtain that there should be something. Give me a moment, okay? So we have this as y, and y is equal to this into 2k plus 3. This 2k plus 3 comes from this, okay? And 4k plus 1, fine. So 4k plus 1, when divided by 4k, so 4 into k plus 1, or rather 2 into k plus 1. 2 into k plus 1 is, or rather 2k plus 2. There should be a square root here, okay? This is square root of 4k plus 1 whole square, okay? This is incorrect. There should be a square root over it. So we see that y is less than x, and thus qk plus 1 is true, and qm is true for all m. And that's how we have proved our requirement. Question 213 says that if m parallel lines are intersected by n other parallel lines, find the number of parallelograms thus formed. To form a parallelogram, we need to select 2 lines from one set and 2 from another. So the number of parallelograms formed is MC2 multiplied by MC2, that is equal to 1 over 4 multiplied by Mn into M minus 1 into N minus 1. Very straightforward problem relatively. Now we move on to question 214. From 6 gentlemen and 4 ladies, a committee of 5 is to form. In how many ways can this be done? If the committee is to include at least 1 lady and 2 particular ladies refuse to serve, there is an extra R on the same committee. So first we compute the number of possible committees. We have 1 lady, 4 men, that is 4C1 multiplied by 6C4, 60. Then we have 2 ladies and 3 men. So this can be chosen in 4C2 minus 2C0, because 2 ladies won't be part of the same committee, okay? That is why 2C0 is there. So this is multiplied by 63 for men, that is 100. Then we pick 3 ladies, and this should be 2 men. This is not 1. So 3 ladies out of 4 can be picked in 4C3 minus 2C1 multiplied by 62, that is 30. And 4 ladies and 1 man, it is not possible. Okay. So that is what 214 is all about. You add this and you get the required number. Now we move on to question 215. A man has 7 relatives, 4 of them are ladies and 3 are gentlemen. His wife also has 7 relatives, 3 of them are ladies and 4 are gentlemen. In how many ways can they invite to a dinner party of 3 ladies and 3 men, so that there are 3 of man's relative and 3 of the wife's relatives? So 3 men from husband side and 3 ladies from wife's side. So this can be done in 4C0 multiplied by 3C3 multiplied by 3C3 multiplied by 4C0 is equal to 1. So we take no ladies from men's side and no men from the wife's side. Then we pick 2 men and 1 lady from husband's side and 1 man and 2 ladies from the wife's side. So similarly, we have this, and we similarly form another group where 1 man, 2 ladies from the husband's side, 2 men and 1 lady from the wife's side. And finally, we pick 3 ladies from husband's side and 3 men from wife's side. So it is straightforward problem, and the final answer is 485. Question 216 says that prove that if each of m points on one straight line be joined to each of the n points on the other straight line terminated by the points, then excluding the points given on the 2 lines, number of points of intersection of these lines is 1 by 4 into mn into m minus 1 into n minus 1. So for an intersection, we need two lines such that they have one point on each of the given lines. Thus, total number of ways to select these 4 points is MC2 multiplied by MC2, which is the given answer. Okay. Question 270 says that John has X children with his first wife. Mary has X plus 1 children with her first husband. They marry and have children of their own. The whole family has 24 children. Assuming that two children of same parents do not fight, prove that missing T is there. Maximum possible number of ways fight can take place is 191. So let Y be the number of children born from John and Mary. So we will have x plus 1 plus y is equal to 24. So 2x plus y is equal to 23. Let Z be the number of fights. So Z would be, you pick one child before marriage from John, one child before marriage from Mary. So xc1 multiplied by yc1. Then you pick one child of John before marriage and one child of John and Mary after marriage. So xc1 multiplied by x plus 1 c1. And then you pick one child of Mary before marriage. Sorry, yc1. Okay, yc1 means one child of John and Mary after marriage, and x plus 1 means one child of Mary before marriage. I think I explained this wrong. So this is one child of John before marriage and one child of Mary before marriage. So eventually Z will be xy plus x into x plus 1 plus y into x plus 1. And we substitute here y is equal to 23 minus 2x. So we get a quadratic equation 3x square minus 45x minus 23 is equal to 0. So if you see this, why there is Z? Z should not be there. No, Z is wrong here. This is 3x square minus 45x minus 23 is equal to 0. Now because x is real, why Z is coming? Oh, Z is total number of fights is here. Okay, I got it. So my mistake, Z will be here. So Z minus 23. Now x is real, so D will be greater than equal to 0. And which will eventually lead to Z being less than equal to 191.75. So greatest value of Z is 191. Question 218 says that find the number of divisors and sum of divisors of 2520. So we do the prime factorization. We have 2520 is equal to 2 to the power 3 multiplied by 3 to the power 2 multiplied by 5 multiplied by 7. So we pick each term of the product. So this would be 1 plus 2 square plus 2 cubed. And then for 3, it would be 1 plus 3 square. And for 5, it would be 1 plus 7. And then 7 would be 1 plus 7. So each term of this product is a divisor of 2520. Thus, total number of divisors is equal to number of terms in the product, that is 48. The sum of divisors we calculate as 9360. It is simple number theory question. Question 219 says that 5 balls of different colors are to be placed in 3 boxes of different sizes. Each box can hold all 5 balls. In how many different ways can we place the ball so that no box remains empty? So the total number of 2 sets of 3 positive integers whose sum is 5 would be 113 and 122. Element of both sets can be arranged in 3 factorial by 2 factorial, that is 3 ways, because we have 2 2's and 2 1's. So that is why 2 factorial is in the denominator. So the required number is 3 multiplied by the ways to place for the first set and then for the second set, which is equal to 150. Question number 220 says that prove that factorial of n factorial is divided by n factorial to the power n minus 1 factorial. So we let m is equal to n minus 1 factorial, so m factorial is equal to mn. So now we have this number. So this we can write as mn factorial by n factorial to the power m, which is the number of ways of distributing mn things among m persons, each having m things, and therefore it will be an integer, and we prove the divisibility. So it was a tricky problem, question 220. Some of the problems require knowledge of certain stuff. So as you can see, the problems are getting harder, so you need to pay more attention. Now I will show you how you can download the book. So you can go to my website ashtavakra.org. Sorry, there is a typing mistake. ashtavakra.org. So you have 3 mathematics books: Algebra, Trigonometry, and Coordinate Geometry. You can download. Coordinate Geometry was uploaded yesterday after yesterday's video. Conic sections are not written yet, and I'm working on conic sections. So you can download Algebra, Trigonometry, and Coordinate Geometry. The link of Algebra and Trigonometry will be in YouTube, and Coordinate Geometry links will come once I have completed it. But you can come to the website and download it. So I hope that you are enjoying this series of videos and finding it useful. And keep practicing and do not wait for my videos. You can go ahead and read the PDF on your own and solve problems on your own. If you have confusion or you want some clarity, you can come back and watch the video, or you can ask questions in comments. You can ask me any problem on 12th mathematics in comments, and I will try to solve them. There is no guarantee though. So with this, I will end this video, and again I thank you for watching the video. Keep practicing, and I'll see you in the next one tomorrow. Till then, I'll say bye to you and keep practicing. So the hotkey does not work.